Last week, I read an opinion piece by a climate scientist who writes, "If you knew what I know, you'd be terrified too." Well, I read it, and I'm still standing upright rather than flat in bed screaming into a pillow. Did I do something wrong? Should I be terrified? Should you be terrified? Should we all be terrified? Let's have a look. I had high expectations when I read Bill McGuire's article on the CNN opinion page. Nothing quite like a little bit of existential dread to go with breakfast. But the only new thing the article taught me is that there was a recent study in the UK which found that, quote, scary images of wildfires and other climate-related catastrophes around the world were effective at cultivating climate anxiety. Oh, great. And that they spurred people to adopt measures that help to reduce emissions. Basically, this climate scientist is advocating that we scare people into action. Hey, let's start a climate horror movie night to save the planet. This mindset is concerningly widespread. For example, also just last week, I saw a press release from researchers at Penn State, which says virtual reality better than video for evoking fear, spurring climate action. And the study findings may help advocacy groups to decide how to best frame and deliver their messages. I'm indeed terrified that scientists support manipulating people. I mean, you expect that from advocacy groups, that they'll try to appeal to your emotions rather than reasoning. But I'd wish that scientists stick with informing people. So let me give you some information about the climate developments in the past month, and then you can make up your own mind about whether it's time to be terrified. The last year was the warmest on record in terms of global temperatures. It also saw a peculiar temperature anomaly in the North Atlantic Ocean, where temperatures went off the charts. The global temperature records have continued into this year, and so has the temperature anomaly in the Atlantic Ocean, though at the moment it looks like at least it's stopped to further increase. Part of the record temperatures can be attributed to a natural climate fluctuation known as the Southern Oscillation that switches back and forth between a warmer El Niño phase and a colder La Niña phase. Last year, we switched to the warmer one. These phases typically last 1 or 2 years, but according to a projection from NOAA just last week, the current warmer phase is weakening already, and it now looks like we're going to switch back to the colder one by the summer. Together with the expected regression to the mean, this makes it somewhat unlikely that this year will be much hotter than the previous one. What's with this temperature anomaly in the North Atlantic Ocean? Climate scientists have considered various possible causes, such as a decline in emissions from ships after a change of law in 2020 or an underwater volcano eruption. However, other scientists say that these influences wouldn't be large enough to explain the observation. So basically no one knows, but clearly it's aliens installing hot tubs underwater. Just wait until Avi Loeb gets on the case. What this means is that at the moment it's unclear whether these are normal fluctuations or an indicator for a trend that no one expected. Some climate scientists say it might be that global warming is accelerating. Some say the observations are still within the range of what to expect if the current climate models are right. In January, I told you that there had been a paper by Hansen and collaborators saying that climate scientists have underestimated the equilibrium climate sensitivity. The equilibrium climate sensitivity, in a nutshell, tells you how quickly the world will warm. The Hansen et al. Study was a reanalysis of old data, by which I mean, fossil records and ice cores and stuff. There has now been another study of data in the more recent past since the 1980s. They confirm that it's possible that current climate models have in bulk underestimated how fast temperatures will increase. It's because many of these climate models aren't particularly good at getting the temperature distribution in oceans right. It's kind of a known problem. In the new paper, they say that this issue with the ocean temperatures has the effect that the real world reacts slower to the increase in carbon dioxide than the models. So if you were trying to fit the model to the data, you'd have to use a lower climate sensitivity, and then you're to get the future predictions wrong. If that's right, then we'll probably see more temperature records soon. In case that was too many words, it's bad news. I feel like we're at a crucial moment in the history of human civilization. This year or next year, we'll find out just how badly we've screwed up our planet. I wouldn't say I'm terrified. I'm disappointed. I'm disappointed that we cause ourselves unnecessary trouble, and I'm even more disappointed that some scientists are contributing to this by advocating that we scare people into action. This might work for some people for some time, all right, but they'll end up feeling manipulated because that's what it is. It's manipulation. Appealing to emotion just increases polarization at a time when we all need to sit together and think rationally about the least bad choice we can make. Should you be terrified? I think you shouldn't let anyone tell you what you should feel. In this week's headlines, I present to you a quantum tornado that supposedly has something to do with black holes. Do they just put the word quantum in front of everything now? No, it's actually a pretty good description. Let's have a look. The headlines are about a new experiment at the University of Nottingham. They used superfluid helium at just a few degrees above absolute zero to simulate quantum effects nearby a rotating black hole. Is this just their idea of fun? Probably, but they had another reason. It's the best way we know to find out how quantum physics works near a real black hole. This quantum simulation of a black hole might sound similar to the infamous headlines of last year about a wormhole in a quantum computer, but it's very different. The wormhole stuff wasn't just a simulation, it was a simulation of a mathematical duality. For this, you first have to reformulate the mathematics and then you simulate that. But because of this mathematical reformulation, the simulation itself doesn't physically resemble the real thing. So there wasn't anything like a wormhole in the quantum computer. A direct simulation, on the other hand, is like this wind tunnel to test aircraft. It's a physical model of the real thing, but one that can more easily be controlled and measured. The new experiment now is a direct simulation, much like the wind tunnel. Of course, they don't create a real black hole either. That'd require even more pressure than nuclear fusion. Instead, they create what's called an acoustic black hole from which sound can't escape. The flow of the superfluid simulates the curved space-time around the black hole, and then they want to measure what the sound does. Though I must add that what physicists mean by sound isn't exactly Beethoven's symphonies. They just mean there are perturbations traveling in the medium like sound travels in air. And since they use a superfluid, the sound has quantum effects, so it's sound quanta that they're after. This analogy between superfluids and black holes isn't just words. The equations are actually the same. This relation is known as analog gravity. The equations are the same provided the medium has a suitable behavior. For one, it needs to be a superfluid, and it also needs to flow in a specific way. That's why they need the quantum tornado. Superfluids have been used before to simulate black holes. The most famous work is that by Jeff Steinhauer at Technion in Israel. In 2015, Steinhauer used a condensate of supercooled atoms to simulate a black hole horizon. In this experiment, Steinhauer wanted to test whether black holes emit radiation, as Stephen Hawking predicted. Hawking made this prediction in 1972. He calculated that black holes must have a temperature that's inversely proportional to their mass, and that means they emit light and other particles. Basically, Hawking said that black holes aren't entirely black. Unfortunately, the temperature of real astrophysical black holes is way too small to be measurable. But if Hawking's calculation was right, then the superfluid analogy of black holes should radiate too, because the maths is the same. And Steinhauer found that his black hole simulation indeed confirmed Hawking's prediction. However, Steinhauer's experiment had a big shortcoming. His black hole simulation didn't rotate. In the real world, black holes rotate. That's just because when matter collapses to a black hole, it's very unlikely to not have any angular momentum. Indeed, as I just told you in a recent episode, the black hole in the Milky Way rotates at 60% of what's physically possible. So in this new experiment in Nottingham, they wanted to simulate a black hole which rotates. That's difficult to do because a superfluid doesn't have friction. That's why it's called superfluid. Normally, if you put a fluid into motion, you start swirling it in one place and that'll drag the rest of the fluid along. In a superfluid, that doesn't work because there's no drag. To get a rotation going in a superfluid, you need to create a quantum vortex. This means you need to set the entire fluid into motion very, very carefully so it goes into a state of high angular momentum. That's the quantum version of rotation, basically. And they indeed managed to get it done. For this experiment, they created the biggest ever quantum vortex in a superfluid. That was a few millimeters in diameter. You can actually see this by eye. This is what they call the quantum tornado. In the middle of the vortex, there's an empty channel. Then they measure the properties of the quantum tornado and also look at how the sound quanta propagate in it. However, they say that to measure these quanta precisely, which is the eventual goal, they'd have to create a vortex that rotates faster. So basically, more work is needed, but still, this is amazing stuff. Of course, superfluid analogies are still very different from real gravity. Mathematically, the most important difference is that the curved space-time which the fluid mimics is not created by response to matter, as it's the case for a real black hole. Rather, it's created by the experimentalists. Conceptually, the relevant difference is that the fluid's correspondence to a curved space-time breaks down once the experiment starts to resolve the superfluid's atomic structure. Fluids, we know, are made of smaller things. Space-time, for all we presently know, isn't. But how certain are we of this? What if the fluid analogy is more than an analogy? Maybe space-time really behaves like a fluid. Maybe it is a fluid. And if so, the experiments with fluid analogies might reveal how we can find evidence for the substructure of space-time. 3 years ago, we saw a lot of headlines about a remarkable experiment at Fermilab in the United States. They confirmed an anomaly of the muon, that's a heavier version of the electron. Their measurement doesn't fit together with the prediction from the current theories. The discrepancy could be evidence that the theory is wrong and that there are new particles or new forces of nature. Or it could mean that the theory is right, but something is wrong with the calculation. So which is it? Theory or the calculation? Well, a new paper now says that it's neither. Let's have a look. The muon is one of the fundamental particles in the standard model of particle physics. It's unstable and decays within a few microseconds. It has a magnetic moment that tells you how fast the particle spins in a magnetic field. Without quantum effects, the magnetic moment of the muon, usually denoted G, should be 2. Physicists are interested in the quantum contribution that's often just called the G-2. The G-2 of the muon can be predicted from the standard model. Just to give you an idea, the prediction is this value, whereas the experimental value is this, and that's why people are afraid of particle physics. How does one measure this? The experiments are basically rings of magnets in which the muons go in circles until they decay, a process that you can also observe in Twitter discussions. But unlike Twitter threads, which just decay into obscurity, muons decay into other particles of which one can measure the momentum, and from that you can infer the G-2. Already in 2001, an experiment at Brookhaven found that the measured value of the muon G-2 deviates from that predicted by the standard model, though it wasn't a huge deviation. In 2021, a follow-up experiment at Fermilab confirmed the earlier result, raising the statistical significance to 4.2 sigma. Last year in August then, the Fermilab group released more data and confirmed the anomaly they'd previously measured. The additional data decreased the uncertainty of the measurement and increased the significance to 5 sigma. That's less than a 1 in 3 million chance of it being a fluctuation. That the statistical significance of the result is now so high means that the discrepancy between the prediction and the observation is very unlikely to be due to a measurement error. It could mean that something is missing in the standard model, maybe new particles or other new physics. And since the standard model contains 3 forces and then there's gravity, which makes 4, in the media they often call the possibility of new physics a 5th force. I explained in an earlier episode what that means. I've always suspected that the discrepancy isn't due to a new force, but a problem with the calculation. This is because these calculations are really hard. It's not just because it's a lot of mathematics, it's also because in parts we don't have the mathematics. So physicists just do the maths approximately on a computer with what's called a lattice calculation. This opens another can of worms, because how do you know that these approximations are even good? And in case you thought that's complicated already, there's another complication, because all these calculations require further input that needs to come from other experiments. So first you need to extract some numbers from other data, and then that goes into your calculation, of which you then do an approximation. And that last bit, the input from other experiments, seems to be the problem. The authors of the new paper have recalculated all these contributions to the muon G-2, and they say there is one in particular that doesn't fit with the data, and that's the process in which a pair of pions are involved. The pions are themselves pairs of quarks, and the data for their properties comes from other measurements, and that seems to bring in an error. To me, this paper is like Sherlock Holmes with maths. It's amazing detective work. But that's not the end of the story. Now they'll have to get better data for this particular process and then redo the calculation to see if it fits. If it does, there's the question whether this wrong number was used for other calculations, which might bring up other problems. So this correction might initiate a shift of other results, which is going to be very interesting. If you've ever encountered humans, you might have noticed that sometimes they're hard to understand. And that means they're kind of like quantum physics. Because, as you've learned on YouTube, that's also hard to understand. And this is why, I guess, a mathematician has come up with the idea of quantum cognition. Yes, quantum cognition. And of course, I had a look. To my surprise, I found that quantum cognition isn't quite as bad as it sounds. It's nothing to do with quantum healing, and it doesn't turn your brain into a particle accelerator either, though that'd be cool, it'd also be kind of unhealthy. No, quantum cognition is about borrowing the mathematics of quantum physics to better understand human thinking. The idea is that this could explain why humans sometimes use reasoning that doesn't follow the rules of classical logic. An interesting example of human irrationality comes from a 2002 study in which an American researcher found that when people were asked whether Al Gore is honest, 68% said yes. Asked afterwards whether Bill Clinton was honest, 57% said yes. But if the participants were first asked whether Clinton was honest, then he got only 50% and Al Gore then got 60%. In both cases, Al Gore came out ahead, but the baseline was lower starting from Clinton. Basically, people don't agree with themselves. So how do you make sense of this? Well, you do it by taking into account that their opinion depends on the order in which you ask the question. This order dependence also happens in quantum physics, and that's what this quantum cognition business is about. A famous example of order dependence in quantum physics is polarization filters. You have a set of polarization filters that leave light through only when it's polarized in one direction. If the first filter leaves through only light that's polarized, say, vertically, and the second one leaves through only light that's polarized horizontally, then no light will go through both. It's totally dark. Now, if you put a third polarization filter in between, then what will happen is that the vertical polarization gets split up into diagonal right and diagonal left. The diagonal right now has a horizontal component. This means something goes through all of them. If you put the vertical filter first, then that doesn't work. So it matters in which order you make these operations. operations. This dependence on the order of operations is often described as a typical quantum effect. But I find this misleading. There are many everyday examples in which the order of operations also makes a difference. It matters, for example, whether you first put on the parachute and then jump out of the plane, or the other way round. Nevertheless, some scientists were thinking maybe this kind of quantum behavior is best modeled by quantum probabilities. Though when I say some scientists, it really seems to be one mathematician at the University of Surrey by name Dodger Brody. He has developed a framework to model cognitive states of mind with wave functions in Hilbert spaces. That is, he models cognition with the same mathematical apparatus that we use for dead and alive cats and so on. For example, in a paper published last year, he looks at the quantum physics of making a choice. Just linguistically, we can see that there's some kind of relation. In quantum mechanics, a system can be in two states at the same time, like Schrödinger's famous dead and alive cat. We call that a superposition. But when you measure it, the state of the system collapses and then the cat is either dead or alive. Now, this is kind of similar to having two opinions at the same time, like whether you want chicken or pasta for lunch. But then at some point the two possibilities need to collapse to just one actuality. Yes, kind of like quantum mechanics, if you go by words. And while this makes for a nice motivation, actually this doesn't come up in the paper. The upshot of the paper is really that certain observations about the probability of making one choice or the other can be modeled with equations that are also being used in quantum physics, like those operations where the outcome depends on the order. Indeed, the author says that he can explain the experiment where people give honesty ratings to Clinton and Al Gore, depending on the order, to within a plus minus 10% error margin. You see, if you want to sound really sciencey, you put an error margin on it. He also says that this formalism can explain confirmation bias. It works roughly like this. You know how a quantum particle can't have a precisely defined position and momentum at the same time. Now, suppose you have a quantum particle that's very well localized. If you measure the position, you get a lot of information about where the particle is. But if you measure momentum, you just learn that it's all over the place. So the author's idea is that if you give information, say a news article, to people's quantum brains, they'll measure different quantities. And depending on what they measure, some will learn a lot, others not so much. And that's all very interesting, but what does that mean? Well, not much. You see, we can also model traffic flowing through streets as if it was a compressible gas made of molecules, but just because the maths is good for both cars and molecules doesn't mean that cars are molecules. And I'm afraid that just because you can use quantum maths to describe some survey results doesn't mean your brain is a quantum computer. What this quantum cognition business means to me is that the mathematical tools that we develop in physics are very versatile and can often be employed in many circumstances. It might well be that some equations used in quantum mechanics can be used to describe human decision-making. This could be, for example, because the brain employs some sophisticated ways of saving energy and time, which is ultimately the origin of our supposed irrationality. But is it irrational to want to save time and brain power? I think not. Then again, I might be irrational. Solar panels and wind turbines are great so long as the sun shines and the wind blows. Unfortunately, that isn't always the case. Our great energy transition, therefore, will need lots of energy storage. You may recently have seen some headlines saying that thermal energy storage is going to save the day. I wasn't terribly excited about those, but then I read about a project that does it with sulphur, and they might be onto something. Let's have a look. Thermal storage is a way of storing energy by first using the energy to create heat and then later using this heat to create electricity. Some systems work instead by using energy to cool and then later using the cold substance to create electricity, but the principle is the same. A difference in temperature can be used to create electricity from it. The most common type of thermal storage uses molten salts. The big advantage over batteries is that it's simple and low effort, which makes it comparably cheap. According to some estimates, molten salt thermal storage is 30 times less expensive than lithium batteries, while reaching a similar efficiency that's well above 90%. The major problem with this thermal storage is that the heat inevitably leaks, so the longer you want to store the energy, the more you lose. Molten salts are good for a few hours up to a few days or a week at most, and this is why I haven't been terribly excited about them. It's a good idea to ease out day-to-day fluctuations, but they won't fix the much bigger problem with renewable energies, which are extended phases of little sunshine and wind, known as Dunkelflaute, that can last up to 2 weeks. But we have a newcomer to thermal energy storage, which is literally hot in the sense that it works at temperatures exceeding 1000 degrees Celsius. The idea is to add a chemical loop to the thermal storage. It's then called thermochemical energy storage. This has been around for some while, but a group from the German Aerospace Center added another twist to it. They store the energy in a stable compound, sulfur, which can last pretty much indefinitely. Basically, you use solar energy to create heat, and that heat is used to perform a chemical reaction that requires energy. You store the reaction products, and if you need the energy again, you let the products react and get the energy back. Concretely, their cycle uses sulfuric acid. With the heat derived from solar energy, you can split off sulfur and water. You collect the sulfur, and if you need the energy back, you burn it. It's kind of like storing energy in hydrogen, except that sulfur is a powder. It's easier to store and handle. While it's not exactly tasty, sulfur itself is of low toxicity, though several of the reaction products are highly toxic and highly corrosive. They say that the process is also more efficient than solar to hydrogen, which has a very low efficiency, dangling around 15 to 20%. According to some estimates, the sulfur cycle could theoretically reach 26%, but there are few studies, and in practice the numbers might be lower. It's also important to notice that this isn't a type of storage that you can use with your average solar power plant or wind turbine. Like most ideas to produce hydrogen from solar, it works with concentrated sunlight. That's when you use a collection of mirrors to focus the sunlight in one spot, where it then gets really hot. This extreme heat is needed to get the sulfur cycle going. That isn't to say that I'm somehow against it, it's just that I don't think it's quite the game changer that the headlines make it out to be. What we'd really need is an efficient way to store the energy of the already existing solar and wind arrays. You see similar headlines popping up every once in a while, like this recent one in the New York Times that mentions a few other newcomers. Like, for example, the company Energy Dome, based in Milan, that fills a huge balloon with carbon dioxide. During the day, solar energy compresses the carbon dioxide until it becomes liquid. At night, the liquid carbon dioxide expands back into gas, which drives the turbine and produces electricity that's sent back to the grid. Or a recent study from Eindhoven University in the Netherlands that says that iron can be rusted and unrusted to store energy and later release it. I could go on for days listing different ideas for how to store energy, but the kids will be back from school in about 10 minutes, so let me wrap this up. These types of storage all have different pros and cons in terms of how long they last or how efficient they are, etc. But at the moment, none of them is both efficient and versatile enough to solve the problem with intermittent energy. If only we had a reliable way to generate energy without carbon emissions, like this thing, what was it called? Nuclear. Thanks for watching. See you tomorrow.